So up to this point, when we've been talking about simple harmonic oscillators, we've pretty much kept it to strictly theoretical. What we'd like to do is we'd like to start throwing a little bit of math in it. So we've talked about things like position, velocity, acceleration, time for these objects undergoing simple harmonic motion. What we'd like to do now is we'd like to start to look at the relationships. And the first one that we're going to look at is acceleration. So we've talked about an object that is undergoing simple harmonic motion. It's going to obey Hooke's law. And we also know that Newton's second law of the net force is going to apply. So for an object undergoing simple harmonic motion, the net force acting on it is just going to be this restoring force of the spring, or we could just say Fs. Now we know definition for net force. We learned it a long time ago. Net force is just mass times acceleration, and then not long ago we learned this definition for the force of the spring. It's going to be negative k times x. Well, we could certainly divide both sides by m here, and then you get this lovely a equals negative kx over m, which we have here. So this equation here, this represents the acceleration for a simple harmonic oscillator. The acceleration, as you can see, it is directly proportional to the displacement, just in opposite direction, which is consistent with Newton's second law. If the force is proportional to acceleration, and we know that force is proportional to displacement for a simple harmonic oscillator, acceleration must also be directly proportional to the displacement. And of course that negative again tells us that a and x are going to be in opposite directions. So this is a way for us to actually calculate acceleration for a simple harmonic oscillator. So we can see here for this oscillator that's moving back and forth about this equilibrium point. So we call left negative, right positive. So when we're displaced left, we have positive acceleration. When we're displaced right, we have that negative acceleration. And again, we can see that negative linear relationship. So acceleration is the easy one to talk about. What we want to look at now, though, is we want to look at that relationship between acceleration and velocity. And it's a little bit more complex. So some of this is going to be a little bit hand-wavy. And as I mentioned earlier, when we do oscillators, we're a little bit restrictive on what we look at. So we know that the force is proportional to x, so we know the acceleration is proportional to x. Velocity is going to be a bit more complicated. Velocity is actually going to change in a non-linear manner. And the reason for that is we have to look again at our acceleration. At the amplitudes, we are going to have the largest possible acceleration. As we move closer to equilibrium, acceleration is going to decrease, and then it's going to be 0 at this point here. And then a is going to be the negative max here, a is going to be the positive max here. So with the acceleration continually changing, the rate of change of the speed is also changing. So the speed's going to change as we move our position in the oscillator. So here's kind of what's going on. Let me look at my graph here. So I have my acceleration graph, and I have my velocity graph as a function of displacement. So at maximum displacement at my amplitude positions, and keep in mind these graphs are meant to line up perfectly with one another. So I'm just going to make a dashed line here and a dashed line here. So at maximum displacement, I have maximum change in velocity. Now what that means is, as the velocity is changing, this thing is going to have a large velocity to start with, and it's going to have a very significantly large slope. Like if we look at the slope of this graph, it's going to be significantly large. But as we go on as a function of time, the acceleration is starting to decrease. What that means is the rate of change of the speed is also slowing down. So as we kind of look at the slope of this thing, as we get closer to equilibrium, it's starting to slow down and slow down. Like this thing picked up speed really fast, but then it's picking up slower and slower and slower. And then when we're at the point where acceleration is 0, this thing is going to be at the fastest possible speed. Now as we move past equilibrium, we are going to start to increase our acceleration in the opposite direction. So we're increasing the acceleration slowly. That means that our speed is going to start picking up in the opposite direction slowly. The slope is changing slowly. But then as we move along and that acceleration gets bigger, this slope here is going to get bigger and bigger and bigger, and we're going to pick up speed much faster and faster and faster. So that's the main thing with the velocity that makes it a bit more complicated. Because the acceleration is changing, the velocity is going to change in a slightly more complex manner. So if we want to be, how would I phrase this? It's changing in more of a quadratic manner, but you don't actually need to know that right now. As I mentioned, the only places you actually have to know about the velocity are at your amplitudes, where it's 0, and at equilibrium, where it's at its maximum. In these positions here, you don't have to know anything about it. As I said, that requires a little bit of calculus. We're not going to touch that one. That's for later on in your physics career if you choose that. So with that said, because we are focusing on velocities at two special points, the amplitude and equilibrium, we want to focus in more on that. At amplitude, not really interesting. V equals 0, okay, done. What we want to look at is how to find that maximum speed. And we are going to use conservation of energy to help us out here. So there's two special points that we look at, amplitude, equilibrium. So at the amplitude, when we have the maximum displacement, speed is going to be 0 and EK is going to be 0. So we have no kinetic energy at the amplitude, but we have the maximum amount of potential energy. What that's saying is when we have this oscillator stretched out to its farthest point, all of the mechanical energy is in the form of potential energy. Now, we let this thing go, and what's going to happen is all of that potential is going to get converted to kinetic energy. So by the time we get to the equilibrium position here, no stretching means we're going to have no potential energy, but at this point here, we're going to have maximum speed because we have maximum kinetic energy. So what this is telling us is that at the equilibrium position, we can describe our mechanical energy as the maximum amount of potential, or maximum amount of kinetic energy. Now we know through the law of conservation of energy is that the mechanical energy does not change. At this point here, I can describe the mechanical energy as the maximum potential energy. At equilibrium, I can describe the mechanical energy as the maximum kinetic energy. What that allows me to do is if I say that the mechanical energy is the maximum potential, and that max is really important, and at the equilibrium, mechanical energy is just going to be the maximum kinetic energy, well, these are saying the exact same thing. What that allows me to do for an oscillator, and we're ignoring friction, I can say that the maximum kinetic energy of this thing is equal to the maximum potential energy. Maximum is the key word in this one. We're not saying EK equals EP. We're saying EK max equals EP max. So EK is going to be half M and then V max squared since we're dealing with maximum. And then our equation for potential energy is going to be half K X max squared. Because again, we're dealing with maximum. Well, we could simplify this a little bit. The halves are going to go away. So I'm going to get M V max squared is equal to K X max squared. Alright, that looks like we're making some progress. We've simplified it. Let's see if we can work it down a little bit more. Well, first thing is that maximum displacement, we call that the amplitude. So instead of writing X max, we're just going to write that as A. So what I actually have is I have mv max squared is equal to K A squared. Now I have V max squared is equal to K A squared divided by M. So at this point, I can square root both sides. So I get something that looks a little bit like this. So I'm going to get V max equals the square root of K A squared over M. Looks really nice. What we're going to do though, because I have that A squared under the square root, I'm actually going to take it out. Because first of all, just for some math 10c, so we know that the square root of x times y is equal to the square root of x times the square root of y. We can separate those. So what I'm going to be kind of doing here is I'm going to say that the square root of K A squared over M, it's just the same thing as the square root of K over M times the square root of A squared. Well, the square root of A squared is just going to be A, and we're going to take that thing out front. So we're going to get V max is equal to the amplitude times the square root of K over M. So V max is our maximum speed, A is our amplitude, K is the spring constant, and M is going to be the mass in kilograms. Emphasize, this is not on the data sheet. If you want to use this equation, it has to be derived. Again, to get this, you're doing EP max equals EK max. Now, you probably are not going to show all this work here, but yeah, this comes from this statement. So if you want to use that, you need to derive it from there. So basically, it's telling us three things. The maximum speed of an oscillator depends on the amplitude, spring constant, and mass. And if you think about it for a little bit, it makes sense. You know, the amplitude, the farther you stretch this thing away from equilibrium, the greater the force, the greater the change in velocity. So it's going to pick up speed much quicker. Spring constant, yeah, if you have a stiffer spring, it's going to exert a larger force. It's going to give you a larger change in velocity. And then mass, if you have a larger mass, it's going to be much more difficult to accelerate by inertia. So bigger mass, smaller acceleration. And then that smaller acceleration is going to lead to a smaller change in velocity, so you're not going to have as large of a speed. So that's how this is how we calculate the maximum velocity of an oscillator. As I said, we're only looking at the maximum velocity and v equals 0 at the amplitude points. Anything between those, we don't care about.